Hello everyone. So welcome. This is going to be the first video I'm going to be sharing on this page. And in this video, I've decided to preach the gospel of Ramanujan Master Theorem. And the reason for this is because everybody knows I love this theorem. If you follow my solution on this page, I use Ramanujan Master Theorem whenever I can. It doesn't matter if that's not the simplest solution to the problem. Even if I know a simple solution that's like 2 lines, I'm still going to use Ramanujan Master Theorem, even if it's going to take me like 10 lines of solution, because I so much love this result. So hopefully, at the end of this video, you will appreciate the power and beauty of this result. So what does it say? Well, it says the Merlin transform of f of x. So the Merlin transform of f of x is defined to be the integral at point s. It says the integral from 0 to infinity of x to the s minus 1, then f of x dx. This is the Merlin transform, just like we have the Fourier transform and the Laplace transform, whereby the Laplace transform is very popular, especially for engineering students, whereby you do the integral from 0 to infinity of e to the negative st of f of t dt. This is the Laplace transform of this function f of s. For this one here, for more serious integration problems, so that we use Merlin transform. So Merlin transforms, this Ramanujan Master Theorem tells you how to find the Merlin transform of some particular class of function with if you know their series expansion. So it says if you have to find the integral from 0 to infinity of x to the s minus 1 of f of x dx, it says if you know the series expansion of f of x, then you can write this as gamma of s phi of n, phi of negative x, where phi is related to the series transform of f of x. Now, this cannot work for every function. You cannot just pick any function and just say, okay, gamma of s, phi of s. No, the function must have a peculiar series expansion. Okay, and this is how the function should be. The series expansion should be, oops. Okay, the series expansion of f of x should be the sum as n runs from 0 to infinity of phi of n over n factorial. Then you have negative x to the n. There must be a negative in the x here for it to even work, and it must be in this form. If this is right, then the integral from 0 to infinity of x to the s minus 1 of f of x dx, which is the Merlin transform of f of x, would be gamma of s phi of negative s. So if this function can be expressed as in this series form, then it is possible to find its Merlin transform instantly, and this will help you in many working problems on definite integral. It will help you a whole lot. Of course, it has other application in other area of sciences, but we don't care. We're not going to bother ourselves with such things. We only want to learn this so that we can solve some beautiful mathematical problems. So please, let's look at our very first example. Is going to be the famous one we already know. We already know from the theory of definite integral that the integral of 0 to infinity of t to the s minus 1 of, let me use x, of x to the s minus 1 of 1 plus x dx is equals to pi over sine pi s. So we already know this from the theory of definite integrals. So let's see if we can prove this result using Ramanujan Master Theorem. So to begin, what we need to do is that we need to start x integral from 0 to infinity of x to the s minus 1 of f 1 plus x dx. Now this is like the integral from 0 to infinity of x to the s minus 1 of f of x dx, whereby f of x here is 1 over 1 plus x. We already know that this is equals to gamma of s phi of negative s, where phi is related to the series expansion of f of x. So what we need to do, we need to find the series expansion of f of x. So of course, this is well known. This is basically the sum as n runs from 0 to infinity of negative x to the n. Then after finding the series expansion, we need to compare, look at our phi of n, our f of x. This theorem, this Ramanujan Master Theorem only works if f of x has this form, if f of x can be put in the form as n runs from 0 to infinity. Let me demarcate this. Phi of n over n factorial, then negative x to the n. So we already have a negative x to the n on both sides, so we don't have to worry about that. But we don't have a phi of n over n factorial, where phi of n is a function of n. But there's not a problem. We can even fix this. We can come here and say, okay, this is equals to the sum as n runs from 0 to infinity of, then we will say n factorial, then we'll have a 1 over n factorial negative x to the n. Then this n factorial form will not be too useful for us. We're going to put in terms of gamma. So this is equals to the sum as n runs from 0 to infinity of gamma of n. Then you have 1 over n factorial negative x to the n. Okay, so having this result now at our disposal, okay, no, this is not gamma of n, this is going to be gamma of n plus 1, because we all know gamma of n is n minus 1 factorial. So we need a gamma of n plus 1 here. So there is 0. So gamma of n plus 1. Now, having had this result, let's compare it now. You can see that phi of n here, phi of n is going to be gamma of n plus 1. And that is all. We don't need anything here again. So we can go back to our problem and say, okay, so this right here is equals to gamma of s. Then phi of n is phi of n is gamma of n plus 1. So phi of negative s is gamma of 1 minus s. So this, we already know from material of definite integrals that this is equals to pi over sine pi s. So we have already established this result that we dream of doing with the Ramanujan master theorem. So you can see how powerful it is. Of course, you may think, okay, this is a long process, we're doing this and doing that. Yes, maybe long process, but that's because we are trying to explain it. If you already master this result, you're going to be able to do this in your head. You don't need to do all these configurations. You should be able to do it in your head, and it will be like easier than anything I know of. Now let's look at another. I have a note. So I have some notes written here where we have some example we're going to look at. So the first of the example is we're going to look at the integral from 0 to infinity of t to the s minus 1 e to the negative t dt. Now, this is obviously in the form of the integral from 0 to infinity of t to the s minus 1 f of t dt, where f of t is equals to e to the negative t. And we can find the expansion of e to the negative t. We already know this is equals to the sum of n as n runs from 0 to infinity of negative x to the n over n factorial. This is a well-known result. Everybody should know this. So now let's compare it with the form we know from the Ramanujan master theorem, which says f of x should have this expansion, should be put in the form as the sum as n runs from 0 to infinity of phi of n over n factorial. Then you have negative x to the n. So in this, if you can observe, in this case, phi of n will basically be 1. Phi of n here would basically be 1. So that is that. So basically, this means that the integral from 0 to infinity of t to the s minus 1 e to the negative t is equals to gamma of s times phi of negative s, but phi of s is 1, so this is going to be gamma of s, and this is basically the definition of the gamma function. So gamma of s is equals to the integral from 0 to infinity of t to the s minus 1 e to the negative t dt. Now, of course, this may look as not so impressive for you, but this is actually impressive because this tells you that the gamma function is actually a special case of the Ramanujan master theorem. You can see. So, and actually, there's a very famous result we usually use. If you look at my content and you watch my, you see what I post on Twitter, you know that I always use this result. That is 1 over a to the s is equals to 1 over gamma of s times integral from 0 to infinity of t to the s minus 1 e to the negative at dt. Everybody who reads whatever I post knows I use this, especially for series. I always use it. If you are going to solve a problem and this is going to be a key ingredient, I'm going to find that solution because I love this result and I use it all the time. So let's see if we can establish it using the Ramanujan master theorem. So we need to find the integral from 0 to infinity of t to the s minus 1 e to the negative at dt. Now, we know the expansion of e to the negative at. That is, e to the negative at is the sum as n runs from 0 to infinity of negative a t to the n all divided by n factorial, which is going to be equals to a to the um, which is going to equals to the sum as n runs from 0 to infinity of a to the n over n factorial of negative t times negative t to the n power. Now, of course, phi of n is going to be a to the n power. So basically, this is going to be gamma of s, phi of negative s, which is gamma of s and a to the negative s power. So basically, which is going to be gamma of s over a to the s. And if you compare, that is exactly what we have here. If you divide both sides by gamma of s. Yeah, so you see how easy it is for us to establish this result. And this is not related that much, but I'm going to show you one cool application of this result here. Here it is. Let's say we try to evaluate this integral from 0 to infinity of t to the x to the s minus 1, then e to the x minus 1 dx. So let's say you want to find this Mellin transform here. Now, you need to focus on the expansion of f of this. So you can multiply the top and bottom by, so this is going to be integral from 0 to infinity of x to the s minus 1. Let's multiply the top and bottom by e to the negative x. So you have e to the negative x all divided by 1 minus e to the negative x power dx. So this is basically the integral from 0 to infinity of x to the s minus 1. Then you have e to the negative x all divided by 1 minus e to the negative x dx. So we need to find the Mellin transform of this particular expression here. But you notice that this, we can put it in series form in terms of the geometric series. So this is going to be equals the integral from 0 to infinity of x to the s minus 1. Then they have the sum as n runs from 0 to infinity of e to the negative x to the n. Yeah. So now, but the problem now is that you can't dx, because the problem now is that you can't directly use Mellin transform, the Ramanujan master theorem here instantly. And the reason for that is because notice here that we don't have a factor of negative x to the n. So you have e to the negative x all divided by 1 minus e to the negative x. You have it being equal to, you have this being equal to the sum as n runs from 0 to infinity of e to the negative nx, but we don't have, you understand, we don't really have a negative x to the negative x to the n or something, whatever. And this is a key ingredient for using the Ramanujan master theorem. So we can't use this directly. We can't just plug it in directly. Okay, so what we need to do, we need to do this problem in the most direct way that we can, okay? And here, n should be 1 and not 0 because of this first term. We need to recover the first term, because if n starts from 0, you will have a 1, but we start from e to the negative x. So what we need to do is that, what we need to do here is that we need to just do it directly and swap summation and integration. So we have the sum as n runs from 1 to infinity of integral from 0 to infinity of x to the x minus 1 e to the negative nx dx. Now, if you recall what we have just done so far, you can see here that this is gamma of s a to the s. You can see from this what we have done so far. So basically, this would be equals to the sum as n runs from 1 to infinity of gamma of s a to the n power. Yeah, gamma of s a to the n power. So this is basically, now, of course, this sum may look scary, but not really, because gamma of s is a constant. So we can factor it as gamma of s times the sum as n runs from 1 to infinity of 1 over what? No, this is n to the s power, rather. N to the s power. So 1 over n to the s power, rather, not a. So 1 over n to the s power. So this is the definition for the Riemann zeta function, which is zeta of s. So this is gamma of s, zeta of s. So you can see a very nice application of this result here. That is why I love it so much. And I truly admire it. If you follow my solution, I use it whenever I can, however I can. I always use it. That is the first thing I check. If I'm working on series, I try to represent the series in terms of this function. Anything that has anything, I try to find a way to squeeze and smuggle it inside whatever I'm doing. That's how much I have it in my head. You can erase my memory. You're not going to ever erase this formula from my head. Nothing. So now let's look at a very serious example in terms of the poison kernels. So now these are these expressions on the form 1 over 1 plus 2x cos t. Okay, wait, not let me take this out. So you have 1 over nope. Um no. So you have 1 over 1 plus 2x cos t plus x squared. So whenever you are having an integral that has this kernel, I always use the Ramanujan master theorem. It doesn't matter how, if it is the most difficult solution, automatically my brain tells me Ramanujan master theorem. And I've shared so many problems, maybe like up to 5, that has to do with this kernel. And because it has a nice expansion, its expansion is 1 over sine t times the sum as n runs from 0 to infinity of sine n plus 1t negative x to the n. I read this from Loney's plane trigonometry. That was one of the very first time I encountered a very serious series problem. So that is where I learned this formula from. And I was surprised to see it everywhere in most definite integrals. And I was like, wow. So because of the fact that this particular expression, this Poisson kernel, has this series expansion, it makes it almost irresistible to not apply the Ramanujan master theorem. And the reason is that, remember we discussed that this Ramanujan master theorem, which is the integral from 0 to infinity of x to the s minus 1 of f of x dx. Remember we said this is equals to gamma of s and phi of negative s, whereby phi, f of x has this particular series expansion. The sum has n goes from 0 to infinity of phi of n over n factorial negative x to the n. Remember, as I did say this, okay? Now notice that this kernel has this almost similar series expansion. So we are free to use the Ramanujan master theorem on it however we want. And there's a problem I shared on my page. Okay, let's try to see if we can do it. It says we should find the integral from 0 to infinity of dx 1 minus x plus x squared. Okay, no, not even dx like this. It's actually 1 over, so it's 1 divided by times dx all divided by square root of x. So this was the problem shared. And I converted it to this form, integral from 0 to infinity of x to the negative half. Then you have 1 minus x plus x squared. And of course, this dx. And of course, this is related to the Merlin transform, because we can write this as the integral from 0 to infinity of x to the s minus 1 divided by 1 minus x plus x squared. Okay, then dx. Then dx right here. So this is quite related to the Merlin transform. Now we need to find the expansion of this 1 over 1 minus x plus x squared. Now if you compare it with this Poisson kernel we have here, you have 2s cos t. That means 2 cos t. That means 2 cos t here actually is equals to negative 1, or that cos t is negative half, which means we can take t to be 2 pi over 3, and we are fine. So basically here, if we recognize this, we will have that this expansion would be equal to the sum as n runs from 0. Sine 2 pi over 3 is square root of 3 over 2. Okay, so we can use it. let me rule this line here. Okay. So we know that sine 2 pi over 3 is square root of 3 over 2. And this is equals to 1 over sine t times the sum as n runs from 0 to infinity of sine n plus 1 t. No, then you have negative s to the n. So let's use it. All right, at the top here, you have the sum as n runs from 1 to infinity of 1 over sine t. Then you have sine n plus 1 t, then negative x to the n. So this would be equal to 1 over sine 2 pi over 3. Then you have the sum as n runs from 1 to infinity of sine n plus 1 times 2 pi over 3, then negative x to the n. So this will be equals to 2 over square root of 3. This will be 2 over square root of 3 times the sum as n runs from 1 to infinity of the sine of n plus 1, then 2 pi over 3. You have negative x to the n. So this is the series expansion here. Now, we need to remember the Ramanujan master theorem says we need to have a function of n divided by n factorial. Oops. Yes. So remember it says we need to find the function of n divided by n factorial here. So now we need an n factorial here, but that is not really an issue since we can even invent one. We can say this is equal to 2 over square root of 3 times the sum as 0. N runs from 0 to infinity of gamma of n plus 1. Then you have sine n plus 1 2 pi over 3 all divided by n factorial. Then you have negative x to the n. So you can see this, we already have this expansion now. So basically here, our phi of n is equals to, our phi of n is 2 over square root of 3 times gamma of n plus 1 sine n plus 1 2 pi over 3 easily. So we already have our phi of n from the Ramanujan master theorem. So basically the integral from 0 to infinity of x to the s minus 1 minus x plus x squared dx, which is gamma of s, phi of negative s, would be equal to gamma of s, then we have gamma of 1 minus s, then you have 2 over square root of 3 multiplied by sine of 1 minus s, then you have 2 pi over 3. Yeah, that is it. Let's check. Yeah, everything is here. So now all we need to do is to simplify this expression. So then we have this is equals to pi over sine pi s, then you have times 2 over square root of 3, then you multiply sine of 2 pi over 3 minus 2 pi over 3s. So first of all, let's simplify this depending on the value of s. What is the value of s? Let's find the value of s and do everything here. So the question is here, we have a negative half. So s minus 1, we want s minus 1 to be negative half. So basically s would be 1 minus half, which is 1 over 2. So s here is half. So basically we need to, so this will be pi over sine of pi over 2, then multiply by 2 divided by square root of 3. Then you have times sine of 2 pi over 3. S is half, so you have minus pi over 3, which is basically pi over sine pi over 2 multiplied by 2 over square root of 3. Then you have sine pi over 3. So sine pi over 3 is going to be square root of 3 over 2. So this is going to be pi over sine pi over 2 times 2 over square root of 3 multiplied by square root of 3 over 2. So basically everything cancels. Like this is equals to 1. So pi over 2 is 1. So everything boils down to pi. So basically here, this is the problem I solved on my page that day where we got pi as our beautiful final result. So this is it. The answer to this problem is equals to pi. And there are many problems I solved on this related to the Ramanujan master theorem, but all of them are basically the same. You just find the Mellin transform of the integral from 0 to infinity of x to the s minus 1, 1 plus 2s cos t plus x squared dx. This is just find the Mellin transform of 1 over 1 plus 2s cos t plus x squared. And we can find the expansion here using we can get the expansion, of course. This is equals to 1 over sine t times what? The sum as n runs from 0 to infinity of sine of negative x to the n sine n plus 1 t. So we can get this expansion and we can put it in this form, 1 over sine t. This is the sum as n runs from 0 to infinity of negative x to the n. Then you have gamma of n plus 1 times the sine of n plus 1 over n factorial t here. So basically here, our phi of n for using the Ramanujan master theorem, our phi of n here would be equals to gamma of n plus 1 sine of n plus 1 t divided by sine t. Now, the Mellin transform now can easily be found from the Ramanujan master theorem, which says the integral from 0 to infinity of t to x to the s minus 1 f of x dx is gamma of s phi of negative s. So in this case, the integral from 0 to infinity of x to the s minus 1 divided by 1 plus 2s cos t plus x squared dx would be equals to gamma of s, gamma of 1 minus s. Then you have sine of 1 minus s times t all divided by sine t. And this right here, this is pi over sine pi s times sine of 1 minus s t all divided by sine t. And of course, you can depend on the value of s. Doesn't matter if they give you to do the integral from 0 to infinity of, let's say, x to the power of 3 over 4. And then you have this 1 plus 2s cos t plus s squared dx. So you can always put the value of t here and simplify. Sometimes it may involve logarithms where you need to take derivative of it. Sometimes, but in that case, when you need to take derivative, it is much more preferable to use Bernoulli polynomials. So this is probably the next video I'm going to make on this page. We're going to discuss the theory, but first, maybe I may do an introductory video, introduce the Bernoulli numbers, and then I'll do the advanced video for Bernoulli polynomials and Euler polynomials. Because when you are taking derivative of this function, even for the first derivative, you are going to suffer. Second derivative, I tried it once. I don't think I'm ever going to ever do such things again. Then third derivative. But with the Bernoulli polynomials, it doesn't matter if you're taking fourth derivative, it is easy because all you need to do is just construct the Bernoulli polynomials and just plug in your values and you are just good. So it's just so short and easy. So I'm going to have to do a course on Bernoulli polynomials, obviously, and Euler polynomials, as well as the applications. But for now, let's just enjoy our Ramanujan master theorem. So last example I'm going to give, this is taking so long, but I meant this video to just be long. So anybody don't have to watch it straight. You can just come back to it whenever you feel like. So I'm going to give the last example on this, and that is going to be finding the Mellin transform of sine function. So we're going to find the integral from 0 to infinity of x to the s minus 1, then sine of x dx. So the Mellin transform of this sine function can be found with complex numbers, where you have to write sine of x can be written as the imaginary part of e to the negative ix, I believe so, then you would then have to find this integral will have to be the imaginary part of the integral from 0 to infinity of with this will be not negative ix. Let's say negative ix. It will be negative imaginary part of it or yes, so negative imaginary part of it. So, but let's just forget about the signs. Let's just take this. Then you have x to the s minus 1 e to the negative ix dx. Then you are going to relate it to the gamma function where this is equals to gamma of s all divided by I to the s power. Then you are going to find the imaginary parts of this expression and you should be fine. I think there is one aspect of doing it that of solving this problem. I never used this to solve this problem before because mostly I don't care. Whenever I can solve it with the Ramanujan master theorem, I don't want to know anything about this complex number and how to solve it. I'm very fine with the Ramanujan master theorem and that is all. So here for this problem now we're going to need this expansion of sign. So this is the integral from 0 to infinity of x to the s minus 1. We all know that the expansion runs from n equals to 0 to infinity of there's negative x to the n, then you have x to the 2n plus 1 all divided by 2n plus 1 factorial. This is dx. Now for this, okay, no, let me get a different color. Now for this our problem right here, we really need to get one of the x's out here. So if you take an x out here, you have x to the s, then you would have the sum as n runs from 0 to infinity of okay, what am I doing? No, this is not the form to write it with. Sorry about that. This is actually the form to write it. Says this is equals to x to the 2n plus 1 over 2n plus 1 factorial, then negative 1 to the n. So sorry about that. That was a mistake for me. So I already factored out an x. So we are going to take the s square inside this. So we are going to have the sum of 1 over 2n plus 1 factorial. Then you have negative x squared to the n. So remember for the Ramanujan master theorem, we had a negative x to the n. So we need to make a substitution t equals to x squared. We badly need to. The reason for that is that we need to get a t. So we have a negative t to the n. Then once the substitution is made, it's easy to see that dt over 2 square root of t is going to be dx. So we already have a way for dx. What about for s? Well, since t to the half is x, then t to the s over 2 is x to the s power. What about the limit? The limit is from 0 to infinity, so we are all good. So this will be the integral from 0 to infinity of, okay, there's a half. We need to factor out a half here. Then you have t to the s over 2, and then you have the sum as n runs from. The substitution does not affect the sum. The sum is in terms of n, not s, and not t, not x, or is in terms of n. So this is 1 over 2n plus 1 factorial. Then you have an negative t to the n. See how sneaky we can be. Then you have dt over square root of t. Square root of t is t to the negative half, and if we add it here, we will get s minus 1 over 2. So we would have, this is half times this integral from 0 to infinity of t to the s minus 1 over 2. Then you have n runs from 0 to infinity of 1 over 2n plus 1, then negative t to the n power dt. Now, we need an x to the alpha minus 1 something before we apply the Ramanujan master theorem. So that means alpha minus, that means we need to add and subtract 1. So if you add 1, we have s minus 1 over 2 plus 1. That would be s plus 1 over 2. So let's set s plus 1 to be alpha. So this will be equals to half of the integral from 0 to infinity of t to the alpha minus 1. Then you have the sum as n runs from 0 to infinity. Now we need to take care of this. We need to multiply the top and bottom by gamma of n, because this is actually 2n plus 1 factorial, not an n factorial. So don't be fooled into thinking we are all safe. So we need to multiply the top and bottom by some n factorial. So we have gamma of n plus 1. So we need to multiply. Now this 2n plus 1 factorial, let's bring it out. So you have 2n plus 1 factorial. So you have 1 over n factorial. They have negative t to the n dt. So we are making some progress. We are slowly building it up. This is 0 to infinity of t to the alpha minus 1. Then the sum as n runs from 0 to infinity of. Now we can, this 2n plus 1, can start as gamma of 2n plus 2. So that is gamma of n plus 1 divided by gamma of 2n plus 2. Then you have 1 over n factorial. They have negative t to the n dt. Of course, if you have been following this video, you will know that we now have phi of n, which is that phi of n would be gamma of n plus 1 all divided by gamma of 2n plus 2. So now we can continue our good stuff and recall. We're going to stop here and recall that the integral from 0 to infinity of t to the alpha minus 1 is going to f of t dt is gamma of alpha p of negative alpha. So this, our expression here would be half of gamma of alpha times gamma of 1 minus alpha all divided by gamma of 2 minus 2 alpha. Then you will have, yeah, that is that, nothing again. So now we can simplify things a little bit. We know that gamma of 1 minus alpha is pi over sine pi s. So that would be pi over 2 sine pi s. Then you have 1 over gamma of, let's factor out the 2. You have 1 minus alpha. So we know alpha, right? Alpha is s minus 1 over 2 or something. Okay, alpha is s plus 1 over 2. So let's make do with that. Okay. So we know that alpha is s plus 1 over 2. So basically, 1 minus alpha is 1 minus s plus 1 over 2, which is basically going to be 2 minus s plus minus 1 over 2, which is 1 minus s over 2. So basically, 1 minus alpha is basically 1 minus s. So we have a 1 minus gamma of 1 minus s here at the bottom. Okay. Then here you have so this would be half of pi over sine of s is alpha plus alpha is okay, this is alpha though. Alpha is s plus 1 over 2, so that you have this was alpha. So you have an s plus 1 over 2 times the pi, then you multiply it by 1 over gamma of 1 minus s. Now the sine of s plus 1 pi over 2, we can simplify it over this side. So you have sine of s plus 1 over 2 times pi, which is sine of pi s over 2 plus pi over 2. That would be sine of pi s over 2 cosine of pi over 2. This goes to 0. And then that would be plus sine of pi over 2 cosine of pi s over 2, which should be cosine of pi s over 2, because this is basically equal to 1. So then we will have okay, then here we'll be having we can multiply top and bottom by gamma of s though. So you have pi over 2 cosine of pi s over 2. then you have gamma of s times gamma of s gamma of 1 minus s. So that would be equals to pi over 2 cosine of pi s over 2 multiplied by, this is pi over sine pi s, so we can just flip it and get sine pi s gamma of s all divided by pi. When the pi's cancel out, then we can factor gamma of s, so we have gamma of s, then you have sine pi s all divided by 2 cosine of pi s over 2, and then we can write this as gamma of s. This this is 2 sine of pi s over 2 cosine of pi s over 2 all divided by 2 cosine of pi s over 2. So we can cancel this. So we can cancel the 2. So you have gamma of s, then you have sine pi s over 2. So this is the Merlin transform of the sine function. And we can safely conclude that the integral from 0 to infinity of x to the s minus 1 sine of x dx is equals to gamma of s times sine of pi s over 2. Okay, so we can. This is basically an introductory course on the on the Ramanujan master theorem. We can solve other advanced problems, of course. You can share them with me under the comment section, and we can look at them. In the future, I may decide to elaborate on this, like solve more advanced problems, but maybe such things may happen. We don't know. But for now, I believe this is enough for you to solve many problems on definite integrals using the Ramanujan master theorem. So thank you for watching this video, and please do follow me. Thank you. I appreciate it. Thank you very much for following up. Thank you.